Okay, let's talk about tension. It's time to talk about tension. Time to talk about tension. So tension. Let's lay this down. Okay, so tension is a manifestation, one of our four fundamental forces, and it is the electromagnetic. Okay, so it is electromagnetism at the heart that is the cause of a tension. Okay, so it's under the umbrella of electromagnetism. So the question is, what is it? Okay, so we have, say, some object with mass, okay, in a gravity field, and that object is like hanging from the ceiling, and it's hanging from a cable. We'll draw this cable, and it will be a brown cable. All right, and of course that doesn't line up. Let's just move it there. All right, so this represents a cable with an object with mass hanging. So, when we had an object sitting on a surface, we talked about how the force of gravity was opposed by the normal force, and that in a case like this, F net equals 0. So we know that the upward and the downward forces have to be equal. Well, the same logic applies here. You have a gravitational force on this object aiming towards the Earth, okay? And there's no normal force now because it's not sitting on a surface, but there is a cable attached here, right? So it's this cable that is going to be providing the upward force. And a force pulling in a cable, we call that a tension, okay? So we'll just label that as F sub T for tension. And this, of course, is F. It's not an F. F G, okay? Or weight if you want. Okay, now this is the upward and opposite version of that, okay? And how is this electromagnetism? Well, essentially, your cable is made of molecules. I don't know what your cable is actually made of, but let's just imagine that a molecule might look like this. And if you attempt to, and it's lots of these, like so strands of molecules, right, of some sort. It could be a metal cable, so it could be actually strands of metal. But basically, as you attempt to pull these apart, all right, their chemical bonds stretch and resist that pulling apart, and that is a manifestation of electromagnetism. Okay, so that's a fairly straightforward example. If you knew the mass of this, you could quickly find the tension here, right? But where it gets more interesting is if these tension forces are acting at angles, okay? Because then a little bit of math comes into play. All right, so let's imagine that instead of hanging straight up and down, we've got a box on here, and we can take some lines here, and we can attach cables like so. Okay, and we can throw in some angle, and at first we'll make them equal. Oops, let's get that away from there. Okay, and we'll say then that theta in this case is equal to, we'll call it 40 degrees, okay? And we'll say that this is a 25 kg mass. And we'll say that these two thetas are equal to each other. And what else can we say here? Yeah, find Ft in each cable. Okay, so mathematically then, we're going to have to use some vector components here and analyze how these vectors are going to look, okay? So we've got this. Weight is equal to mg, okay? And if we look here, we can imagine that there is tension forces that look like this and like this, okay? They're pulling upwards in this direction. And then we could think that there must be some like components of these things, okay? So we've got a leftward and a rightward component of this, okay? And then we've got an upward component and an upward component. Let's just arrange this correctly. And let's just like label these so we know what we're talking about. Call this force of tension, and we'll call this Ft prime, okay? So this theta value actually is going to transfer down to here as well, right? So by internal angles, you know, when you're crossing parallel lines, these end up being equal. All right, so what do we know? Well, we know that Ftx is there, okay? And we know that Fty is there. And we know that Ft prime y is here, and that Ft prime x is here. Okay, so that's components of tension, right? So the x and y components of my tension force here. And so now we can start to say some things. So we could say this. Well, we know there's no acceleration left or right, so there's no net force left or right. We could say that Ft prime x therefore must equal Ftx, okay? And if those two are equal and these angles are equal, then by trigonometry, we know that Ft and Ft prime have to be equal. All right, because if you have two sides of a right angle triangle, they have the same angle and they have the same component here, you cannot help but have equal values there. All right, so this is a proof that these two have to be equal when the angles are equal. Okay, and then the other thing we know is this, that the weight is shared equally, right? The weight is shared equally by Fty and Fty prime. Fty and Fty prime. Okay, and the other thing we know about this, right, if these angles are equal, these hypotenuses are equal, well, these values are equal. Okay, these values are equal. Okay, so if these two values are equal, we could then say that half the weight is equal to one of these things. So we'll just pick one. Okay, half the weight is equal to one of these things. Does that make sense? If these two values are equal to each other, then half the weight is equal to one of them. Okay. All right, so so how are we going to sort that out then? Well, we don't actually want the y value. I mean, we could figure it out. What we're really after is the tension, right? So let's just work over on this side. Okay, so we're going to work over on this side. We'll say this: Ft, right, sine theta. Ft sine theta is equal to Fty, right? Does that make sense? T times the sine of theta is equal to Fty. So then we could take this formula and we could substitute that in. We'd say this: half the weight should be equal to Ft sine theta. Okay, or 1/2 mg equals Ft sine theta. And what we're really after is this value right here. So rearranging that formula then, Ft equals 1/2 mg divided by the sine of theta. Okay, so 1/2, the mass was 25 kgs, times the value of g, 9.8 meters per second squared, divided by the sine of 40 degrees. And the tension then should be equal to, so I get 190.6 newtons of tension in each one of those cables. Okay? So 190.6 and 190.6. Now, what do you think happens to the tension as we say these are on like little pivots, and we start to pull them farther and farther apart? What would you suspect is going to happen to the tension? Yeah, it's going to increase, absolutely. Okay, if we drop these right down to 0, then each of these cables is just holding half of the total weight, right? About half of 250 roughly, okay? But as you like move out and out and out, right, the tension is going to increase and increase and increase, okay? Yeah, so that's, I think, fairly straightforward, solvable. Let's take it to the next level. All right, so let's try a new one here. We'll give this a mass. We'll call this, well, let's call it 25 kgs again. We'll give this, so what this represents then is like, you know, maybe a plant or something strung up like this, or a sign, maybe even a signpost. And we've got a tension cable here. We've got a tensioned cable here. All right. How are we going to sort out then how this all works? So we're just going to jump right in. So start to draw your like free body diagrams on here. Draw where your forces are all aiming. So you've got, you got your weight. Oops, that's not very good. You got your weight aiming down here. Okay. Now we're going to look here, right? So this tension right here cannot support any of the y value. Can't support anything in the y direction because it's perfectly horizontal. So there's no y component of this one. So in other words, this this tension here is providing all of the upward y lift that we need. Okay, so we're analyzing this. You can just go ahead and say, okay, so a component of this tension force must counteract weight and it must lift the entire weight, right? So we would say then that this component, so we'll call this FTY, must be equal to mg. Okay, it's got to be equal to mg. That's the only place you can get anything in the y value from this setup. And we'll put an x component there. Okay, so we'll call that FTX. And this FTX must be exactly equal to FT, right? So we put some arrows on here. This tension will be provided in a leftward direction because this tension is up and to the right, and therefore its components aim like this. So let's just write down what we know, right? We know that FTX is equal to FT prime, okay? And we know that W is equal to FTY. We also know that FTY is equal to FT sine of theta. Okay, FT sine theta. So now we can solve it, right? So we would say take this here and just sub in what we know. So weight is mg. Mg is equal to Ft sine theta. Okay, so then Ft, in this case, is mg divided by the sine of theta. So we've got 25 kgs times g divided off by the sine, I think I said it was 30 degrees this time. Yeah, divided by the sine of 30 degrees. This will give us our force in newtons on our Ft. So I get 490 newtons for that. Okay, so that's Ft. Now let's do Ft prime. So we know that Ft prime is equal to Ft of x, and Ft of x is equal to Ft times the cosine of theta. Okay, so then Ft equals, sorry, Ft prime equals Ft cos theta. So Ft is 490, cos 30 degrees. You get about 424 newtons. Okay, let's try one more, even slightly maybe more involved here. So we have to get our thinking caps on for this one. Yeah, that's right, I said thinking caps. Deal with it. Put a weight here. This represents a weight. Maybe it's a plant hanging from some wires. I don't know. But what happens if our tensioned cables are now no longer at equal angles? Because we could probably imagine a scenario where they maybe would not necessarily be at exactly equal angles. Oh, let's call that something different, hey? Okay, so let's say you know this. Say that's 40 degrees, and say this is 30 degrees. We've got Ft, got Fp prime. Let's make this, I'll stick with 25 kgs. And so now it's a little more tricky, okay? So I think how we'll deal with this is we'll split it up like this. You got to remember here, oop, I don't like that, I want a straight line. You got to remember here that the actual geometry of, and the sizes and lengths here are not the same as the forces, okay? So in other words, like we can make these ropes shorter or longer and still have the same forces in them. All right, so the lengths of the rope are not representative of the sizes of the force. Okay, so you have to keep that in mind. And then we got to think about how we're gonna like set this all up. All right, so nope, don't like that. So step one is let's see if we can free body diagram in the forces that we know of. Okay. All right, so we got mg down. Okay, we've got kind of like two upward components here, right? We've got FTY and we've got FT prime Y summing together to counteract the weight. Okay, and then we also have, let's see if we get a different color here. We've got FTX aiming that way. We've got FT prime X aiming this way. So let's say what we can say here. We can say this. We can say that FTX must be equal to FT prime X, and that each of these does a little bit of lifting, but it's going to be an unequal share now. They're not going to each be lifting half anymore because the angles are different. We can't say that they'll be each lifting half, but we definitely know that these two things are equal, right? We know that because there's no acceleration left or right. This object is sitting still. So then we could say that the weight must be counteracted by Ft prime y plus Fpy. Okay. All right. So we're not really interested in the values of these x's. What we really want is Ft and Ft prime. So we're going to write these in terms of Ft and Ft prime. Okay. So Ft prime of x, we're actually going to find as Ft prime times the cosine of theta, right? And then we're going to define Ft of x, right, as Ft times the cosine of alpha, right? So let's rewrite this in terms of that. Ft prime cos theta must be equal to Ft cos alpha. Okay, and then let's do the same thing with our y values. So I'll just write them over here because there's more room. Ft prime y should be equal to Ft prime sine of theta. Okay, and Fty should be equal to Ft sine of alpha. So then we should be able to rewrite this. I'll just put it right underneath here. We'll say weight is equal to Ft prime sine theta plus Ft sine alpha. All right, so now as it stands, both of these formulas, right, have two unknowns in them, okay? However, if I take a look here, I see that I could say have a Ft prime here, but I could put it into terms of Ft, all right? So what do I mean by that? Let's just take these and move them down and have a look at how I could maybe construct a system for working with these things, okay? So let's put this little formula that I made here in terms of Ft prime, for instance. So it could be the other way around, but you could say then that this is like saying, Ft prime should be equal to holy, why do you keep trying to tease? Ft cos alpha divided by the cos of theta, right? And if I look over here, I see an Ft prime here, and if I can replace Ft prime with something in terms of Ft, I should be able to solve because then I only have one unknown. So what we're going to do is do a substitution. Substitute. All right, so then we get this. Once we've subbed, we get W equals Ft cos alpha over cos theta times the sine of theta plus ft sine alpha. Cool. Now we have a solvable problem, right? We can solve for ft using this. So let's isolate ft. Okay, so algebra time, right? So weight equals, all right, so this ft appears in both of these, so you could then say ft is alpha cos theta sine theta. Look at all the trig all over the place, plus sine alpha. All right. Then we just rewrite it to make it look a little nicer. That. So one other thing we can do to help compress this is we know that sine theta over cos theta is the same as tangent of theta. So you could then do this. And then you can rearrange and solve for ft. Ft should be equal to W over cos alpha tan theta plus sine alpha. Okay, let's put in some numbers, see what we get. Ft should be equal to mg cos, I forget what my numbers were, cos alpha, 30 and then 40. Okay, see what we get. I'll just have to do some calculation. This happens to work out to be 1. Sorry, just rechecking. It's actually, I just put it in wrong. It's 1.22. There we go. Okay, perfect. And that agrees with what we did before. So this is legit. Yay. So I get about 199.7 newtons. Okay. So 199.7. And actually, we don't have to go all the way through that whole thing for the other side, although you could. If we know that what ft is, we could find ft prime based on this formula, right? So we could then just take this number and say ft prime equals ft cos 30 divided by cos 40 degrees. So this is ft. We should be able to solve for ft prime just using that. So this gives us 226 newtons. So do 26 there and 199.7 there. All right, that sort of maybe more or less does it for those types of problems. And we'll end there.